All right, howdy everyone. We'll get started. We'll give you the most amount of time as possible to ask questions during this. So welcome. Thanks for coming. We'll have this for an hour and a half. We'll probably finish up a couple minutes early in case anyone has individual questions they need to ask. And then tomorrow at 9 a.m. I'll do another Zoom review. I'm just traveling tomorrow, so I can't do the evening one. With that being said, I do have an alarm going off because I need to check into my flight. So when that goes off, just let me do that real quick. And then everything today and tomorrow will be recorded and posted, and then you can watch that on the links. I'll send an announcement if you need to review any of that. Exam Friday just during class time, and it should cover everything up through what we did Monday with Le Chatelier's principal. I think that's all I have for announcements. Are there any questions on exam 2? Okay, what questions do we have content wise that we want to see? Could be anything, general exam, mock exam, something else, anything you would like. Yeah.
Question for another one.
Okay, so when we look at question 3, we have an ammonia reactor that performs the balance reaction below is initially filled with 50 atm of nitrogen and hydrogen and 20 atm or 200 atm of ammonia gases. After equilibrium is reached, temperature stays constant. The equilibrium partial pressure of NH3 is 196.3 atm. And we want to determine Kp for this reaction. Okay, so the important thing to note here is that we're solving in Kp, right? So we just need pressure units. All of these are given to us in ATM already, so we don't need to convert anything between Kc or Kp, okay? So what is the first thing we're going to do with this problem? Yep, we can set up the initial. So I always start with my ice table here. I tend to rewrite the equation just to give myself a little bit more space. Everything is gaseous, so I'm just not writing that there, but I know that I have to include that into my equilibrium constant. I rewrite it so that if there is a solid or a liquid or something you can't include, I'm not writing that down when I'm doing my ice table. So we'll start our ice table. We're saying that we are starting with 50 atm of nitrogen and hydrogen and 200 atm of ammonia gases. So where do those numbers go? Yep, those are all going to go under I. What do we put underneath ammonia? That's the 200. Then we have 50, and then we have 50. Okay, at this point, I want you to ignore everything else in the question that's being stated about equilibrium being established. I just want to know which way the reaction is going to proceed. Do we know that based off of what's given in our question? Yes, right. If we were to solve for Q here, there is no K that we can compare that to. So we have to be given information in our question. What do we know about the final pressure of ammonia? Is it greater than or less than our initial? It's less than. So what does that mean our change has to be? It has to be negative, right? If we're just having less reactant than what we started with, that means that we had to use some up in our reaction. So we know that we have to have a negative for our change for ammonia. And what is that going to be if we were just going to term given this X or whatever? It has to be 2X. Yep. So what does that mean for nitrogen and hydrogen? Plus X and plus 3X. Okay, so then at equilibrium, we're going to have 200 minus 2X, 50 plus X, and 50 plus 3X. But we're given that we have 196.3 ATM at equilibrium. So that is what this is equal to. So we can say 200 minus 2X is equal to 196.3 because I know my equilibrium partial pressure is 196.3 for my ammonia. And this right here, this 200 minus 2X would give me that pressure of ammonia. So then we can solve for X and we can have X equal to 1.85. And how does that help us? Yep, we can plug that in for our pressures of N2 and H2. So we'll have 50 plus 1.85, which is 51.85. And then we'll have 50 plus 3 times 1.85. And that is 55.55. And then we know that this is 196.3. So how do we solve for KP after that? Yeah, we can just plug it into our capital K or our equilibrium constant. So if we were to write that out generally, what goes on top? Products, and what are those? N2 times H2 to the power of 3 divided by NH3 squared. So then this becomes 51.85 times 55.55 cubed over 196.3 squared. And we should get C for KP. What questions do we have on 3 still? That makes sense how we solve that? Does that help your question? Great. Okay, what else? I guess I have more questions. Is this product or reactant favored? Why is a product favored? It's greater than 1, yep. Your K reaction will technically always be positive. It's just, right, it'll always be greater than 0. It's just, is it less than 1? Is it between 0 and 1? Or is it between 1 and a million? Or 1 and infinity, excuse me. Okay, so you have a big K or a small K, but it should always be positive. If you get a negative K, just check your math again. If the volume were to increase, is this going to go towards the reactants or products? It will go towards products. Can someone tell me why it's going to go towards products? Technically that is correct, but that's not why it's going to go towards. Yep, so there's more moles of gas on your product side. So if volume is increasing, all right, our pressure decreased, right? So that's the correct statement there. But we need to replenish that pressure that we now lost. Okay, so in order to replenish that pressure, we need to go to the side that has more moles of gas so that there's more molecules in our system afterwards. Okay. Yep. Yes, if it was asking for concentration, then it would now be Kc, and they would probably give you starting reactants. Or you would solve for Kp and then use the Kc formula and solve for Kc that way. Right, if they asked this the same way, but instead of determine Kp, they said determine Kc. You're gonna solve for Kp and then use the Kp is equal to Kc formula. Yep. Yep. Any other questions on 3 before we move on? Okay. So for 6, we have the flashing of fireflies is the result of a chemical reaction, and the rate of flashing can be described by the Arrhenius equation. A certain batch of fireflies were observed to flash with a rate constant of 16, 1/minutes at 25 degrees Celsius, with a rate constant of 5.5 at 15 degrees Celsius. Use these data to find the apparent activation energy for the reaction that causes the flies to flash. Okay. So what equation do we need to use here? Yep, the Arrhenius equation, we're going to use the combined Arrhenius equation. This is given to you, so you don't have to memorize it that way. And it is given to you as ln of K2 over K1 equal to EA over R times 1 over T1 minus 1 over T2. So and in case you forget to look at your equation sheet, you should remember this is that it goes 2, 1, 1, 2, or as it goes 1, 2, 2, 1, right? As you read it from down and to the left, you want your numbers to be sandwiched. So you want either 2's on the outside and 1's in the middle, or 1's on the outside and 2's in the middle. It does not matter which one you correlate 1 to 2, as long as they match, right? As long as if this is K1 and this is T1, that's all that matters, as long as they are coordinated together. Okay. And then this would be K2 and this would be T2. Okay. All right. So then you can just plug in what you want for this. Or plug in what you just showed. So K1 or K2 we said was 5.5 over 16. It's equal to EA over R. And we have 1 over, we need to change our Celsius into Kelvin. So then we have 1 over 298 minus 1 over 288. And what R are we using? Say it again. So we're gonna use the one that's 8.314 because this is in joules per mole Kelvin. So we want that energy component, right? We're solving for an activation energy. We need the R that shows us our energy units. I would recommend solving for your ln, keeping that on your left-hand side. I would recommend combining your temperatures, keeping that on your right-hand side, dividing by R, and then dividing by whatever that is. I did this slightly different, so my notes are just a little backwards, so I don't have these numbers. Right, so I combined my temperatures there first. I'm then going to divide by 8.314. And then I'm going to divide by the negative 0.00014. So EA I got to be 76,194.75. What units is this come out to be? Joules per mole. So how do we get to kilojoules? Divide by 1,000. So your activation energy is 76.2 kilojoules per mole, which is going to be D. Everyone understand the math that happened here? I highly recommend, unless you have like a fancy calculator, you have this one. I recommend a lot of parentheses. You can do a fraction. Godspeed. I'm jealous, but yeah, use parentheses when in doubt so you don't screw up a fraction. That makes sense for 6, whoever asked that. Yeah. Yep. Yep. Any other questions on 6 before we move on? Everyone knows, I'm sorry, before we do 6, everyone knows how to get rid of the ln function if necessary, right? For solving for a reactant, you have to do the e to the power. Okay. I think I gave that on the week 5 practice problem. So if you don't remember, I think it's question 7 or something like that. So you can do a practice there. Okay. For question 5, we have the following reaction is useful obtaining cleaner fuels from coal. We're given that. And then we have at a certain temperature, Kp is equal to 2.4, and if 0.16 moles of carbon, carbon monoxide, 0.54 moles of water, 0.62 moles of carbon dioxide, and 0.48 moles of hydrogen are put in a 2-liter flask, which of the following statements is not true? Okay. So whenever I have questions that I say are true or not true, I like to go through each of them. And even if I find the answer that I think is going to be it, I like to prove the other ones true or false, depending on what the question is asking. Okay. So we'll start from D and go to A. That tells you what the answer is going to be. So for question or for answer choice D, we have Kc is equal to Kp. Is this going to be true or false? True. Why is it true? Perfect. Yep. So our equation here is that Kp is equal to Kc times the RT to the delta N, and N is going to be the moles of products minus the moles of reactants. So Kp is equal to Kc times RT. Is our equation balanced? Yep, it is. Our equation is balanced, so we have 2 moles of products minus 2 moles of reactants. This becomes 0, which makes our exponent 1, which makes, I'm sorry. This becomes 0, which makes our exponent 0, which makes that RT portion 1. So this means that KP is equal to KC. So that answer choice is true. We're looking for something that is not true. So this is not going to be our answer. Okay, questions on answer choice D? For question, or for choice C, we have QC is greater than KC. How would we check that? Just solve for Q, right? So Q is going to be the same setup as K. We have CO2 times H2 divided by CO times H2O. Q is 0.62 times 0.48 over 0.16 times 0.54. And Q is equal to 3.78. How does Q compare to K? Q is greater than K. So is that choice true or false? This is true, right? So this is true, so this is going to be not our answer. Okay, and then for choice B, we have to reach equilibrium, the concentration of H2 will decrease. Is that true or false? Yep. Yep. So we do. In this case, and in my notes I did. In this case, everything's being divided by 2. It's all going to be the same. If this were an ice table, yes, you would have to change it. But because all of these are being divided by 2, it's not going to make a difference here. So this should actually be, that's a great point, 0.34, 0.24, 0.08, and 0.27. It still comes out to 3.78. Okay, but Q is still greater than K. And then, so then to reach equilibrium, H2 will decrease. What do we say for that one? Yeah, that's true, right? So if Q is greater than K, which way do we have to go? We're going towards reactants. And if we're going towards reactants, that means we have to use some of our products to form those reactants. H2 is a product, so that concentration will decrease so that we can form more reactants. So this is going to be true, which means that A should be our choice, but let's just prove it. So to reach equilibrium, carbon monoxide will decrease. Where is carbon monoxide, a reactant or product? It's a reactant, yep. And what did we say we're forming more of? We're forming more reactants. So we should be increasing our concentration of carbon monoxide in order to get Q equal to K. So this will be false, which is not true. So this will be our answer choice A. Okay, does that make sense for 5? Any other questions on 5? Yep, so we plugged in all of the moles given. So I plugged in the moles directly. Everything gets divided by 2 because for KC we need concentration. So, right, like this one here, the concentration of H2 is 0.48 divided by 2. So that's 0.24 molar. So we can plug in all of those concentrations to K. Since we're given every reactant in every product, then we have all the information needed. We can just say these are what's given to us at the time that they are all combined. So which way do we have to go? Right, so that's where the 3.78 right here comes from. And then we're given that KP is 2.4, but we know KP is equal to KC. So we know that Q is greater than K. Any other questions? Great question. Yep. Yep. So we said that Q is greater than K. So if Q is greater than K, we have to go towards reactants. Right now we have too many products. So in order to produce more reactants, we have to use up some of our reactants and make more, or sorry, we have to use more of our products and make more reactants out of them. So if we're using stuff up, then we know that our concentration has to decrease at equilibrium because we have to use up some of those products to make those reactants. Okay, so to reach equilibrium, H2 will decrease. That's true because Q is greater than K. We have to make more reactants. In order to do that, we have to use the concentration of some of our products to make them. Does that make sense? Okay. Yeah. Yep. Before I do that, if you need a visual for that, right, you can think of right now at equilibrium, we have, this is where equilibrium should be, but we have more products. So I like to think of this as going to fall. So in order to fall, to make that all level, we need to produce some of this. So we need to shift towards the reactants. And so we need to use up some of this extra stuff here to make it level with our reactants. You want to visual it that way? I don't know. Sometimes helps me. Okay. You said 11. Okay. So we have the reaction 2N2O5 goes to 4NO2 and O2. Follows the rate law below at 60 degrees Celsius. According to the rate law below, the reaction is blank order with respect to N2O5. And if the initial concentration of N2O5 is half, the initial rate will be blank. Okay, so if we are given the rate law, can we get our reaction orders directly from this? Yes. So if we're given our, where do we get our reaction orders from? Where is that housed? Units is one of them. Where else can we see? The exponent. Yep. So our exponent here tells us what our reaction order is going to be as well. What is our exponent if it's not there? 1, right? We need 1 as our exponent. So what does that tell us the reaction order is? This should be first order. And let's check it with our units. What is our units on our rate law or rate constant? One over seconds. Does that match a first order? Yes, it does. Yep. Right, and if we use the shortcut I showed, 1 over m to the overall minus 1, right, we get time seconds, and this becomes 1 over m to the 1 minus 1, which is 0, which is time seconds, which is just 1 over seconds. So that matches. Okay. So if we have a first order rate law, if our concentration is halved, what happens to our initial rate? It's also halved, right? So we should have C as our first one. If we have a first order reaction and our concentration is doubled, what happens to the rate? Also doubled, right? If it's times 1,000,000, what does our rate do? Also times 1,000,000, right? It should be the same increase in concentration and rate or the same decrease, right? If it's going by half or by a third or something like that. It should do the same exact thing for your rate as well. If it was second order, how much, and we were having it, how much would our rate go down by? 1/4. Yep. If this was 0 order and we halved our initial concentration, what would happen? There is no change, right? If with 0th order, it doesn't matter on the concentration, right? We're just worried about the rate. It's going to be, the rate's going to be the same. All right, any other, yep. Yep. Any other questions on 11? That help? All right. So for question 2, the elementary steps for the reactions B2 to C2 goes to B2C and C are listed below. What is the overall rate law for this reaction? And we're given 3 steps here. So what step determines our rate determining step? Or which one is our rate determining step? This slow reaction. Yep. So what step do we write the rate law for? We write it for the slow one, right? We write the rate law for the rate determining step because that tells us, right, it doesn't matter about the other steps along the way. We have to get through that slow step in order for the reaction to happen. Everything else is going to be fast. So the rate law is determined by the rate determining step. So how are we going to write the rate law for step 2? What does the rate law start with? Rate is equal to, right? K. What goes into it? Yep, and then your reactants. Do we need to solve for anything in terms of rate law or in terms of reaction order? No, where does that come from? The coefficients. So we have AB2 times C2. So it should be B, right? No, nope. Why it cannot be B? There's an intermediate, right? This intermediate can't be in rate law. So how do we get rid of that then? Nope. I like your thought, but no. Yep, so we need to take advantage of the equilibrium that's in step 1. So what do we know if something's at equilibrium about the forward and reverse reactions? Their rates are the same, right? So if we were to write a rate law for the forward reaction and for the first reaction and for the reverse reaction, we'd have rate times, we'll call it K1, A times B2. And we have rate is equal to K2 times AB2. And what can we do with those 2 rate laws in red? We can set them equal to each other, right? The rates of the forward reaction is equal to the rate of the reverse reaction. This, the K2 times AB2, is telling us that that's equal to the rate, which must be equal to whatever's happening in the forward direction. So we can set K1 times A times B2 equal to K2 times AB. And then what can we do from there, right? We're trying to get rid of AB2. What can we do? Close. We're gonna solve for AB2 and plug it in to our initial slow step rate law. So this becomes AB2 equal to K1 over K2 times A times B2. Right, we can't have the concentration of AB2 in our rate law. So we're going to plug something in that shows us what it would act like, because the forward and reverse reactions are the same in our equilibrium, and that's where our intermediate is produced from. So then we can take this whole thing and plug it into our concentration of AB2 from our initial slow step rate law. Sorry, there's a lot of arrows going on here. I ran out of space. So here we'll now have rate equal to K, our first initial rate constant, times K1 over K2 times A times B2 times C2, sorry. Now this K1 over K2, right, those are all rate constants. They're all coefficients. They're all numbers. We can combine all of them, and that becomes our K observed. So this goes to rate equal to K observed, A, B2, C2. And what answer choice does that correspond to? This is now D. Yep.
The individual step, intermediate one.
No. Right, an intermediate can never be in a rate law. Catalyst can, so that's why A is allowed to be in our overall rate law. But an intermediate cannot show up in an overall rate law. So I don't think this is going to show up, right? But if your slow step was third, then you would have an equilibrium in your second step and an equilibrium in your first step. So you would have to do this twice to solve for that concentration of the intermediate. I don't think you'll see that. That's pretty complicated. But right, it is possible for the slow step to be third. I think I put this on week 6 additional practice problems on question 3, I think. So if you need to do another practice of that one, there is one there for you there. Okay, does that make sense why second step and everything you have to do for that one? Yep. Yes, yeah. So if this was slow, then your rate law would just be rate is equal to K A times B2. And you can move on from there. Yep. When you combine them, they're still doing that math. So it's just being multiplied and divide. So you don't have to there's no special rules like capital K with exponents or anything. You could just multiply and divide them normally. I don't think you have to solve for K at all. But if you were given a concentration, you could do it that way. Any other questions? Yeah. Any other questions on 2? Alrighty, so for question 9, we have reactions 1 and 2 have been determined to have the following equilibrium constants. We're given the 2 there. and using the equilibrium constant values above, determine the equation or the equilibrium constant value for the following reaction 3. Okay, so you can think of 3 as like your overall equation that you're trying to get to, and we're breaking it down into steps 1 and 2. So what do we need to do to get from 1 and 2 to 3? What do we notice first? Say it again. Yep, so we need to double 1. So if we look at D2 here and 4D here, or sorry, we 2D and we have 4D here. In order to get from 2 to 4, we have to multiply by 2. So we're gonna times 2 for our reaction. But what does that mean for K? K goes to the power of 2. So K1 to the power of 2. Does that fix equation 1? Yeah, we can stop there. So we'll do that. We'll have 4D goes to 2B and 2E. And K1 becomes 8.41 times 10 to the negative 8th. Remember that small numbers, as in decimal point, should get smaller when you square them, and then large numbers should get bigger when you square them. Square them, not square them. Okay, so that fixes 1. Is 2 good? No, what do we need to do for 2? Yep, we need to flip this. So what does that mean for K2? That takes the inverse or the reciprocal. So this is 1 over K2. So then we get 2B gas plus 2C goes to 2A. And K2 becomes 1.758 times 10 to the 5th. And then again, if you have a small k and you take the reciprocal, it should become a big K. If you have a big K and take the reciprocal, it should become a small k. And then what do we do in order to get to 3? We have to equal, or you have to add our 2 equations. Should this have a 2 in front? That should, oh no, we just left it, never mind. So then what do we do to our k's? We multiply them together. So we should end up with D. And then I think we said it should be 0, 148, not 148. Is this product or reactant favored? It's reactant favored, yep. I don't think you'll ever have to do this, but if you were subtracting your equations, what would you do to your k's? You would divide them. Usually you can just add them up. You don't need to subtract, but. Let's help with 9. Okay. What else? Yep. Alrighty. So for question 13, we're given experimental data and we're asked to find the rate constant K for this reaction under the equilibrium conditions. Okay. So this is your method of initial rates. And how do we look at our method of initial rates? Or how do we use this chart? We're using this to find our order, right? We're looking at how does concentration change and then what does that do to rate? So we're looking for cases where only one reactant is changing and the other reactants are staying the same. So if we're starting with A, in what two experiments is A changing, but your other reactants are staying the same? 1 and 4. So between 1 and 4, as we go from 0.1 to 0.2, what happens to our rate? Right, this goes by times 2. What happens to rate? Also times 2. Okay, so if we're going times 2 and times 2, what does that mean about concentration of A? What is the order for A? Should be first order. Okay, what about for B? Yep, 3 and 4. So as we go from 0.12 to 0.24, what are we doing? How do we get from 0.12 to 0.24? That's times 2. What happens to our rate? This is times 4. So if we're going times 2 to times 4, what is our order here? This is second order. And then what about C? One and 2, we go from 0.15 to 0.3. What do we do here? This is times 2. What happens to our rate? Nothing, no change. So what does that mean for C? That's 0 order. So if we were to write the rate law, what would our rate law look like? Bless you. Rate is equal to K times concentration of A times concentration of B squared. Okay, notice how our coefficients in front of A, B, and C do not match the exponents or what our actual rate law is, right? We need the experimental data in order to determine what the orders of our reactions are. Okay, how do we solve for K once we have this? Perfect, right? We can take any experiment you want. It could be 1, 2, 3, or 4. And we'll plug in the rate, bless you, for, and then our other concentrations. So I did 1. And I got K equal to 3.5. And then what should our units be? They're all the same. It doesn't matter. It should just be B. All right, but you should have 1 less concentration. So molarity to the -2 over hour. Right, and if we did 1 over molarity times overall order -1 times seconds, what is our overall reaction order for this? It's third order, right? So we have 1 over molarity 3 minus 1 times seconds, or I guess this is hours. So you have 1 over molarity squared times hour, which matches that. Okay, when in doubt, if you can't see just based off of times 2 or times 4, you can always write the rate law for that experiment. So you can always write between 1 and 4. So the rate of 4 is equal to K4, or I guess K, times 0.20 over X times 0.12 Y times 0.15 Z over the rate of 1 is equal to K times 0.1 X 0.120 Y. Sorry, we should have used this one. So if you divide these, then your K's cancel out. Anything that is holding the same concentration cancels out. And then you can combine this to say 0.01 over 0.005 is equal to 0.20 over 0.1 to the X. Right, and then you can see that 2 is equal to 2 to the X. So what does X need to be to get to 2, right? You can look at it that way as well, if you can't see it directly from just saying times 2 or times 4. If you divide 0.01 divided by 0.005, you get 2, and if you divide 0.2 by 0.1. So then you're looking for what exponent of X would give you 2. So 2 to what power gives you 2? Right, so, and then that would tell you the exponent, which matches the first exponent for A there, right? That correlates to that. And then you could do the same thing for the other, like from 4 to 3 for reactant B, and then from 1 to 2, or 2 to 1 for reactant C. And you would see that like the Y exponent comes out to 2, and then that the 0, or the Z exponent comes out to 0. Okay, talk to yourself for a minute. Okay, what's next? Yep. You could be. And so that's where like this rate portion of dividing would come into play. Because if we're given a change where, right, you would solve for the thing that's never held constant first. Find that order, because then when you're given this portion here, let's say that B was never held constant at some point, then for the Y's, you could plug in the 2. And then you can solve for whatever that would have been that way. Yes, you would then probably have to use log in order to get that number. But I think we're gonna give you cases where it's you don't need to worry about that. Yep. Yep. Mm-hmm. As long as that reactant is the only thing changing, right? If we were to pick, if we were to pick these two here, right? If we were to pick 2 and 3, right? In 2 and 3, A is doubling and B is also doubling. So that means that that rate is changing based off of both the change of A and B. We don't know which one it applies to because it could be either one that is causing it, right? So we want to look for the experiments where everything else is being held constant. That way we know that whatever is changing for that concentration is or whatever that rate is changing by is the result of that change in concentration. Does that make sense? Okay. Right, so I wouldn't pick like experiment 1 and 4 to find A or C. Yep. Mm-hmm. Okay, so for 12, we have considered the aqueous equilibrium reaction between iron 3 and thiocyanate ions, which forms iron 3 thiocyanate complex. Okay, which of the following statements is true? So again, we are going to prove that all of the other ones are false. Okay, so for A, we have if heat is added to the reaction mixture at equilibrium and Fe3 plus and SCN minus increases, the reaction must be endothermic. How are we going to determine that one? For a reaction to be endothermic, what does that mean for heat? Is that a reactant or is that a product? It's a reactant, right? So I want you to think of heat as delta H as another reactant. Okay, so if iron 3 plus and thiocyanate are going to increase in concentration, did that mean that we went towards reactants or products? We had to go towards reactants. If we're going towards reactants in endothermic reaction, do we need to increase or decrease heat? We need to decrease heat, right? In order to, we need to decrease this way so that we can have our arrows head to tail. So if the equilibrium of that is increasing, if the equilibrium of iron and thiocyanate increases, the reaction must be endothermic, right? And heat is added to the system. What would happen if it was endothermic? It would actually go towards products, right? So this is going to be false. Because if the reaction was endothermic and heat was added, then we actually should see a decrease in the iron and the thiocyanate ions. Does that make sense why A is false? If heat is added to the reaction mixture at equilibrium and iron 3 plus and thiocyanate increases, the reaction must be exothermic. So now what happens here? What did we do? Where did we put heat as a reactant or product? As a product. And we're adding the reaction mixture. So what's increasing, products or reactants? Products. So which way does our arrow go? Towards reactants. We're going towards reactants. What happens to our concentration of iron and thiocyanate? Increases. So does B look promising? It does. I wouldn't stop here. Let's prove our other ones false. When water is added to the reaction mixture at equilibrium, the concentration of thiocyanate will increase and reestablish equilibrium. Do we care about water? Nope, because what is water? It's a liquid. It's like adding H2O liquid to our system. Do we care about liquids for equilibrium? Nope. Right, what's actually going to happen is that all of their concentrations are just going to decrease by the same amount. So equilibrium does not get disrupted at all. So this is going to be false. And then what about D? When additional Fe3 plus ions are added to the reaction mixture at equilibrium, the concentration of thiocyanate ions will increase to reestablish equilibrium. No, right? Because if we're increasing the iron, what happens to our equilibrium? Which way does it shift? Towards products. So if we're shifting toward products, what happens to our concentration of thiocyanate? It should decrease, right? This will decrease. So this is false. So we proved that B is our correct answer. It means the entire system, right? If you had a beaker of this, right, they're saying they're adding more water to the beaker. Right, you're not just adding it to the reactants, or you're not just adding it to the products. You're adding it to the whole thing. Yep. Yeah, for sure.
And you have like high table you're solving for x. And I don't know, so you have like something x squared over something minus x times something else minus x. So in what scenario would you disregard the exponent? Like,
So if you're so, right, if we have this scenario, then our K becomes 2x squared over 0.1 minus x times 0.2 minus x. Okay, so this would be probably one that you would have to use the quadratic formula from. If your K is less than times 10 to the fifth, the negative fifth, as in it's times 10 to the negative 6 times 10 to the negative 7, right? A bigger negative number, then you can disregard it. Okay, then that means that you can use the assumption rule and this goes to 0. Okay, I think the case is also if you take your initial concentration is greater than, I think, 3 magnitudes of K, then you can also use the assumption. So here, this is 1 times 10 to the negative 1, which is greater than 1 times 10 to the negative 5, right? There's 4 orders of magnitude in between that. So if your exponents are between, have at least 3 apart, then you can also use the assumption rule. Right, so if you started off with 1 times 10 to the negative 2 as your K, but you started off with 100 molar of it, right? That's 1 times 10 to the 2 and versus 1 times 10 to the negative 2. So those are 4 magnitudes different. You can use the assumption there. Yep. That is negligible, right? In order for solving for x. Then that means that, right? So then that means you can solve for x easily, but at equilibrium, the x is actually, you would say the concentration is using that x that you solve for, right? So you would disregard x in that denominator, you would solve for x. Let's say x is 1 times 10 to the negative 6, right? 1 times 10 to the negative 6. If you're solving for the concentration, you're going to say 1.0 minus 1 times 10 to the negative 6. And it's going to be that actual concentration at equilibrium. It's 0.099, right? It's pretty close to 0.1, so that's why we can assume that it's kind of negligible when solving for it, but it's actually just a little bit soft. Yes. One more thing before I say that. There's also a 5% rule. So if you solve for x and if you divide that, if you take x divided by your initial and it's greater than 5%, then that is also then you can't use the assumption. So if you take whatever your x is divided by initial value times 100, if this is greater than 5%, you can't use assumption. Say it again. Which assumption? Where x in the denominator is 0. Yep. You would just get a more accurate answer. It would be like the answer that you get if you assume and the answer that you get if you don't assume would probably be off by like 0.0001, right? Like it's pretty essentially the same if you wouldn't notice it, which is why the assumption would work in that case. It's just so you don't have to use the quadratic formula. Yep. Yeah, most likely not. Like most likely you're either going to be able to square root it in order to make it solve easily. I would be surprised if she would make you decide the assumption rule was in play or not. But if you see that later on in life, you can use that here. And it might come into play for like acids and bases moving in. So good to be familiar with it now. Yep.
On the denominator.
Yep.
But like in the numerator, it's the same number. Why is it not negligible?
Because so we are starting with the concentration of your reactants here. What it's saying by saying that the denominator is negligible for x is that at equilibrium, so little of that product is produced that the change in concentration looks almost exactly the same. Like if you were to round it, it would probably round to your initial concentration again. However, it is still important or non-negligible in the numerator because some product must be produced. If you don't produce any product, it's 0, and then that doesn't match, right? Then Q is 0, Q is less than K. So you have to produce a little bit of something in order to make Q equal to K. Does that make sense?
Yep.
Okay. Great questions. Anything else? Yep. Right, 10 first and then 15. Yep. Okay. For 10, which of the following statements correctly describes the reaction that generates the following graphs? Okay, so we're given 3 different graphs. We have concentration versus time, the ln of concentration versus time, and 1 over the concentration versus time. Okay, so again, right, we're going to prove that one of them is true, the other ones are false. So for A, we have the reaction is 0 with order in NO, and the slope is equal to, or K is equal to 0.0002, and the half-life is about 80 seconds. Is this true or false? False. Why is it false? Right. Concentration versus time is not a straight line plot. The straight line plot will tell you the order. So which order should this be? It should be first. So before we even continue, right, we know that it should be first order. So this is false. We know that this is first order. Okay. So what else can we eliminate? We can also eliminate D, right? We know that this reaction is not second order. We know that it's first order. All right, so then what's the difference between B and C? Yep, so for B and C, one of the K values is negative, and then we have different half-lives, okay? Can K ever be negative? No, right, your rate of reaction can never be negative. There always has to be something towards producing a rate. So yes, it looks like, according to your slope, y is equal to mx plus b, that your slope should be negative k, but it's a negative k, right? This is negative k. So you want to take the negative of the negative. So k is just the positive portion of this, which is the 0.0084. So it should be C. Let's prove that it's C, right? So this is false. No neg k. So let's prove that it's C. How are we going to prove that our half-life should be about 80 seconds? You can plug it into the half-life formula. T1/2 for first order, does anyone remember off the top of their head? ln2 over k. And if you plug that, you get T1/2, I think about like 82 seconds. So that's about 80. That checks out. Does that help? All right, the only one, so for 0th order, if that's the straight line plot, again, that's y is equal to mx plus b. You have a negative k as your slope. So you want to take the positive version of that. The 1 over n2 is second order. That one already comes out to be a positive k, or your positive slope. So you can just take the number directly from that. Okay, any other questions on 10? 15. So we have the reaction between nitrogen gas and oxygen gas to form nitrogen monoxide does not produce much nitrogen monoxide even at high temperatures. Kc for the reaction below is 4 times 10 or 4.10 4.10 times 10 to the negative fourth at 2000 degrees Celsius. What is the equilibrium concentration of NO when 0.5 moles of N2, 0.5 moles of O2 and are introduced to a 1 liter flask at 2000? Okay, so how are we going to solve this? We need to do, excuse me, our ice table. Does anything need to be disregarded in our equation? Nope, we can use all of them here. So we have N2 gas plus O2 gas goes to 2NO. We have ice here. What goes into our initial portions of our ice table? 0.15. Yep. So we do technically need to make this into concentration, but we're just in 1 liter, so it does just stay as 0.15. But this is 0.15 for both of them. Do we have any initial NO? Nope. Which way does our reaction go? Towards products. Right, because if we were to solve for Q, what is Q at initial? 0, right? Q is 0. So anytime you have 0, you're always going to make products. But in this case, right, Q is less than K, so you have to go towards products. So at equilibrium, we have 0.15 minus x, 0.15 minus x, and 2x. So then when we solve for K, we have NO squared over N2 times O2. So this goes to here, where we have 2x squared, the entirety of 2x, not just the x, 2x squared times 0.15 minus x and 0.15 minus x. If we were talking about all of our assumption rules, right, if we're looking at the value of k, right, is our exponent meet that rule? No, right, we said times 10 to the negative 5 or smaller. So this is times 10 to the negative 4. It doesn't work that way. And then is our magnitude different by 3? Like barely not, right? We start with 4.1 and then we have 1.5. I think that's technically 3 magnitudes. It would probably work, but it's a little too close for comfort, because what can we do instead in order to make this easier for us? It's the perfect squares on the bottom. So we can have 2x squared over 0.15 minus x squared. Then we can square root both sides. Right, this is equal to 4.10 times 10 to the negative 4. So then we can square root there. This goes to 0.02 times x over 0.15 minus x. And then you can distribute and just solve for x that way. And x should be 0.003 molar. Yeah. So then the equilibrium concentration is what? Should be 2 times that. Is that answer on there? No, right? It's just 2x. Did I mess up? Oh, I messed up. I messed up. I see what I did wrong on my answer key. Oopsies. This is 2x. This is equal to x. So that is so x is equal to 0.0015, and then we need 2x, which is 0.003. Sorry. If you made a mistake and just said plus x like I did, it came out to 0.3 exactly, or 0.003 the first time you solved for it. So I still got the right answer, but it should be 0.0015 for your concentration of x. Then you have to multiply by 2 to get to your concentration of N2 or NO. Does that help you with 15? How would you solve for the concentration of N2 or O2 here? Yep, so you just take 0.15 minus 0.0015 to get your values there. Okay, any questions? I mean, I would say it's probably pretty similar to, like, you had what? 3 on the mock exam, 3, 4 on the mock exam, probably similar amount there. Yeah, yep. And when in doubt, it's multiple choice question. So if you set up your ICE table and then start plugging numbers in, then like you can find it that way too, right? You could always take all of those concentrations and plug them in to see if you solve for K that way. Question? Yep. Okay, so for question 8, we have consider an equilibrium reaction X and Y at 300 K with KEQ equal to 10 to the negative 4. Which of the following statements is true? Okay, so at 300 Kelvin, the equilibrium mixture is composed of mostly products. Is that true or false? That's false. Why is it false? K is less than 1, right? K is less than 1, so that is reactant favored. For B, we have at equilibrium, the forward reaction is no longer occurring within the reaction mixture. That's false, right? What happens at equilibrium? The rates are equal, but the reactions are still happening, right? If the concentration of X is equal to 0.105, then the concentration of Y is equal to 0.055, the reaction will proceed to make more reactants. How would we solve that? We have to solve for Q. So Q is equal to Y over X, which is 0.055 over 0.105, and that is 0.5238. How does that compare to K? It's bigger, which is bigger than 10 to the negative 4. So Q is greater than K. So which way do we go? More reactants. So this is true. Oops. True. And then at equilibrium, the rate of the forward reaction rate forward is less than the rate of the reverse reaction rate reverse because K is less than 1. Nope, that's false. We know that these are equal. So K forward equals K reverse. Because at equilibrium, the rates are the same. So our answer is C. Yep. 4. Any other questions on 8? If you're asked for, is this product or reactant favored? So if it's reactant favored, you'll have a larger denominator, which means that K will be less than 1. If you have a K bigger than 1, that means you have a larger numerator. And so that means it's product favored. Okay. So a substance undergoes first order decomposition. After 40 minutes at 500 degrees Celsius, only 12.5% of the original sample remains. What is the half-life of the reaction at 500 degrees Celsius? So there's 2 ways you can solve this. I'm going to show you the easy way, and then you can figure out the hard way. So the easy way is that you have 100% to 50% to 25% to 12.5%. So we went through 1, 2, 3 half-lives in order to get to 12.5%. So we can take 40 divided by 3 and we get 13.3 minutes. Technically, yes. If I said that 10% remained, then I would say, okay, 100 to 50 to 25 to 12.5 to 6.25. If 10% remains, I'm here, right? I still went through 3 half-lives. I didn't totally make it to the 4th half-life yet. So I'm looking for something in between my 3rd and 4th half-life. So I would take 40 divided by 3 is 13.3 and 40 divided by 4 is 10. I'm looking for somewhere in between 13.3 and 10. The hard way is with your integrated rate laws. So I would do the ln of AT is equal to negative KT plus ln of A. And I would then plug in 0.125 K times 40 plus the ln of 1. And I would solve for K and then use K in my T1/2 formula of T1/2 equal to ln of 2 over K. So you can check it that way. Does that help for 4? Okay, I think this is a good stopping point. If you have any other questions or individual questions, please just ask me. If you can't make the review session tomorrow, but there's still something that you would like to see, send me an email and I'll make sure I cover it. I think like 10 people said they could show up, so I'm probably gonna be like asking for questions that people need. So if there's something that you want to see that we didn't get to, let me know and I'll make sure I cover it tomorrow. Other than that, good luck and I'll see you next week. Thank y'all.